So we'll start with modern machine vision or modern computer vision, which basically is deep learning, basically using deep learning as a tool for solving computer vision problem. So you already have some introduction to computer vision. So I will give a quick introduction, and then we'll move on to the basically deep learning related problems. So this is what the goal of computer vision is, that we have an image and we want to interpret the image. So generally when we see it, we see the objects in the image. We see that the train has basically crashed through the station. But when you see in the computer, like when we capture it on the image sensor, then this is what it looks like. So it's basically measuring the intensity at each pixel. And so if we just look at this, even if we look at this, then it will make no sense in the sense that if you just look at the numbers. So basically the goal of computer vision is that we should interpret this array of number or matrix as we do in real life. So which is basically interpret as a train crashing through a station. So that's the goal of computer vision. And so basically we want to extract meaning from pixels or collection of pixels. And there are two kinds of tasks which is handled in computer vision. One is called semantic information, another is metric. So semantic basically means that, for example, if you look at this image, so what do we see in this image? So generally we can see that, generally this is how we see it. We see sky, we see building, we see whatever, portrait, and cars, buses, banners, street lamps. So this is how we look at, right? When we see it, this is how we interpret it. And so basically this is object categorization, or basically saying that this image is made up of these objects. So this is a semantic task. I mean, making sense out of the image, basically. And there are other things also. For example, we can also look at the scene, overall scene, not just individual objects, but overall scene. For example, we can say this is an outdoor scene, and this is a city scene with traffic and all these things. So this is like you're basically doing a summary of the whole image. So these, apart from that, you can also do something called image segmentation, where you can try to categorize each pixel, each individual pixel, into object category. For example, this pixel should belong to the category of building, and that way you can do for each of these pixels. So these are all semantic tasks. So whether it is object recognition, object detection, or overall scene categorization, or it is image segmentation, all of this comes under semantics, where basically you're making sense out of the image. The other category, other task that we are interested in is basically using vision as a metric or measurement device. Here, what we are interested in, for example, we are interested in depth, how far the objects are from the camera. So generally, this is used, this has many applications. Generally, it is like you capture two images, stereo pair, and then from there you can compute the depth. And this is another basically related thing, is called structure from motion, where the goal is that, so generally if you're doing stereo, the camera positions are known, and all you have to do is find the depth. Whereas in structure from motion, the camera positions are also not known. So you take it's like take a video camera and just move around the room. And the goal is that we should be able to reconstruct the 3D structure of the room, as well as we should be able to say the position of the camera, how it exactly moved in the room. So that's called structure from motion, where basically you have to estimate both the 3D as well as the motion of the camera. 3D structure as well as the motion of the camera. And there are similar versions. For example, instead of we moving and collecting the data could come from internet collection. So for example, you can just search for Taj Mahal, and it will give out a lot of images. And the goal is that use all of these images to actually reconstruct Taj Mahal, something like that. So all of this, the thing is that we are interested in measuring. So we are using this computer or using the image as a measurement device. So it need not be one image, it can be multiple images. So these are generally the two tasks. Either we can use vision for semantic or for metric. Okay. So, and these are some of the challenges that we face in doing these tasks. For example, there could be a lot of viewpoint variations. So it's the same object, but when you view it from different views, it looks very different. For example, we are very good at face recognition. But if you just rotate the face 180 degree or image 180 degree, then it will be very difficult to recognize. So like that, variations, these variation, viewpoint variation is something which is a challenge for doing computer vision tasks. Then there are other variation like lighting. So for example, it's the same scene, but lighted by different sources, light sources. So you can see that they look very different. So though they are the same scene, still they look very different. So it's lighting is something like these are the parameters which are like a nuisance parameter. We don't want them. Like it depends on how you're defining it. For example, if all we care is detecting this penguins, then this lighting is a nuisance. Like it's not, it is basically something which we want to avoid, but we cannot avoid as such. So same way scale also, like same object can occur in very different scale. So how do you tackle this problem? So if you're interested in detecting persons, the person can be in various shapes and sizes, and then how do you learn a detector which can actually do it? So that's also one of the challenge we face. Then deformation also. For example, it's the same horse. Like let's say I am interested in detecting a horse. So detecting means putting a bounding box. But the same, I mean, it's the same object, but it comes in various shapes because of this motion, because of this deformation motion. So it's not a rigid object, but it is a deformable object. So that also leads to the challenge. Then occlusion could be like one object which we are interested in is occluded by another object. And the occluding object could be anything. We are not interested in that. We are interested in that, let's say the horse. But in front, it could be anything. And then how do you still recognize or detect the horse? So this is another challenge. Background clutter is also another challenge. For example, I am interested in recognizing or detecting this organism, but how do I do it when these are all so much of clutter? So these all adds to the challenge. For another is motion blur. So because of movement, there is a blur. And now it's very difficult to recognize what kind of bird this is. So same way, defocus could also be another of the, for example, I'm focusing somewhere, but the object is further away from that focal plane, then the object will be blurred. And then how do I recognize it? So all these are various challenges that needs to be solved. And there is also this intra-class variation. So all of these are chairs, but they look very, very different. And still we want to say that all of them are chairs. So intra-class means within class variation, so much of within class variation. Sometimes it might happen that within class variation is more than between class variation. So how do you then do classification? So these are all the challenges we face. And so basically the goal is that whatever algorithm we say, the computer vision algorithm, it should be somehow able to, the goal is that these are kind of nuisance parameters, all this illumination, viewpoint, deformations, then this kind of intra-class variations. They are nuisance in the sense that we don't want them. All we care is to, let's say, recognize the object. So how do I do it? So basically, we have to develop algorithm which is robust to this kind of nuisance parameters. So that's the goal, computer vision. And this is the kind of evolution that computer vision has gone through. So obviously, if for example, all we care is to recognize this image, which means all we want to say is this image is nothing but corresponds to bus. So how do I do it actually? So the first step, the most easier or naive way of doing it is just learn a classifier. Take this image and learn a classifier and directly ask it to classify into bus or some set of classes you decide, and ask it to classify among those set of classes. But then this is very difficult. Very difficult to train such a classifier. Main reason is that, again, all the variations it can have, illumination, shape, viewpoint, all these variations. So same bus I can look from the back, front, side. Then it could be night, daylight, and all this. There could be occluding car. So how do I recognize it across all this? So it's not easy to do. Directly using the image without any processing and just passing it to classifier. Classifier is machine learning, right? But so basically this means there is no vision component to it. You're just using a machine learning tool, which is a classification, and then passing it and asking it to. Obviously, it's not going to do. So not going to do well. So the other option is to do some kind of a processing. These are basically the yellow blocks are the vision task or vision algorithms. So you do some kind of a processing before passing it to the classifier, which will finally do the task. So this is what people generally first try at edges, because at least edges are less susceptible to illumination. For example, if you change lighting, the edges generally don't change. So this, if we extract edges from it and then classify it, at least it is invariant to illumination. At least that we can say. It's not invariant to viewpoint, but at least it is invariant to illumination. So like this, if we can, so then comes that generally people, generally the settled idea was around edges, but it was like instead of directly doing edges, you can do histogram. So there was a hog and sift. The hog is the histogram of oriented gradients. So in here, instead of directly taking the gradients, we take the orientation of the gradient, angle of the gradient, instead of taking the magnitude, and then putting it through a histogram, and then doing it. So basically, it developed, like vision was developing like this, more or less, before the advent of deep learning. So basically, the idea was that try out various modules and pass the image through them before finally giving it to the classifier. And the goal of all these modules is to make it invariant to all the nuisance parameters, and to obviously extract information which are invariant to all these nuisance parameters. So that's what the goal was. But what we can see is there is a trend in the sense that these processing basically stages, the number of stages we had was increasing. So it was going deeper and deeper. So now the question is that these kind of algorithm, they are very much, it requires a lot of domain knowledge, right? You have to look at the images and see what features I should extract such that it is invariant to all this illumination viewpoint and all these nuisance parameters. So, and people kind of settled on edges, histogram of oriented gradients, and all those kind of things. So, but it requires a lot of domain knowledge. To develop this algorithm, it took 20 years almost for people to come to a state where it is doing well. So, but what if we can replace this with generic components, or which requires less domain knowledge? What if we can just, and what if we can kind of repeat these layers again and again to get our result? So that's the kind of question, that is basically deep learning, right? Deep learning, you don't need domain knowledge. You have some architectural elements like convolution layers and all, and you kind of stack one after another. You just repeat them one after another. And then finally, you would like to do the task, which is classification. So if we do that, then it doesn't require all these domain knowledge. We can quickly, anyone who knows about these basic elements can then just put them together. And then obviously it requires training data, a lot of training data, and you can train it, and then you will have something which is working well enough. And you don't need this 20 years times to build this, kind of. I mean, here also, so it's like using the power of data and some architectural elements, and then repeating it to get the end result. So here also, like if you think, this also requires data in the sense that when we are coming up with these layers or modules, we were looking at the data and trying to find features which are invariant to certain parameters. So it's also required data, but finally we were using our intelligence to find out what this is. Whereas in this deep learning or machine learning, instead of doing that, you just give it the data and let the computer find out what are the right features. So that is the paradigm shift which happened in 2012, 2010. And from there, instead of like basically from 2012 or 2010, the vision got transformed. So instead of trying to develop all these layers, it's basically use the deep, basically modules kind of, deep architecture modules, and then you will get your task done. And the most basic element of this is neural network. So which is basically, this is basically the biological neuron, but this is the artificial neuron. which is trying to simulate what a biological neuron is doing. So in a biological neuron, all these dendrites, they collect information, and then it produces output. So this is kind of analogous to that. So you have some inputs, so x1 to xn, and then the output node is y, and basically you want to do some operations and produce this output. So the model that was proposed is McCulloch-Pitts model, in which all they did is linearly combine these inputs. So weighted linear combination. So W1, X1, so like something like this, W1, X1 plus W2, X2, Wn, Xn. And then finally there is a thresholding. So you decide on a threshold, here it is mu, and say that if it is greater than the threshold, then it belongs to one class. Maybe you can call it class 1. And if it is less than that threshold, then it is class 0. So this is a binary classifier. So this artificial neural is nothing but a binary classifier, which can divide the space into two. So basically, if you look at, this is the basic equation. So a linear combination followed by the thresholding operation. So this is nothing but, it is like dividing. So this is the space. So if we consider x1 and x2, then it is basically dividing this two-dimension space into two regions. One of them is class 1 and the other one is class 0. So it's a binary classification. And it can be used for simple kind of task. For example, AND gate. So AND gate has this kind of logic table where when both the inputs are 1, it will give 1. Otherwise, it will give 0. So if I draw it, like if I draw it, then what we see is like this corresponds to 0, 0. This one is 1, 0. This is 0, 1. And all of them should be labeled 0. And only this 1, 1 should be labeled 1. So this can be solved using this perceptron. Because all you have to do is draw this line, and then in this side, you can call it class 1, and this side class 0. So for simple tasks like this, it can actually, this neuron can do it. Basically, the criteria that requires is that any function which is linearly separable. Linearly separable means I should be able to draw a line and divide and separate the points into two classes. So as long as this is the case, this one neuron can do it. But what if, but the task is more complicated. For example, this is the XOR gate, in which basically this 0, 1 and 1, 0 is 1, 1. So if I plot it, it will look like this. And so here, the perceptron, one neuron cannot do it, because wherever you draw the line, it's not going to do it correctly. So then what is the solution to this? So the solution could be that you can have multiple neurons. So this is one neuron, and then you can combine them. So if this is your input, x1, x2. You can do a weighted linear combination to obtain a node h1. So this is a hidden layer. And similarly, so which basically corresponds to one line. Maybe the line could be something like this, which says on the left side of this line, it is 0, and the right side, it is 1. And then you can design another neuron, which could corresponds to a line like this, which says that on the left side, it is 1, on the right side, it is 0. And then you have to combine these neurons to get the output. So if you do like that and follow it with the AND gate, you will get this correctly. So basically, sometimes for like for a little bit more complicated problem like this, just one neuron may not be sufficient. So what you need to do is use multiple neurons. And the generalization to this is this. So you have this input layer, and the output is given to you. So generally, it's a label. So, and then there could be multiple hidden layers. So in this case, there was only one hidden layer, and this hidden layer had two nodes. But in general, it could have multiple hidden layers with various number of nodes in each of them. And then it can come to the output. And all we need to do is find out the weights. So here also, the task was to find out the weights, right? Generally this. You have to find the weights and the threshold. So this was the task. This is the training task. Testing task, you are given X and you use the weights and the threshold to give out the class. So generally this is what a multi-layer perceptron looks like. So multiple hidden layers. Each layers you decide on how many nodes you would like, and then follow up this with the output layer. So the output layer, it depends on what the task is. If it is a classification, then you can use certain kind like this softmax and all you can use. And if it is a regression problem where, so classification is there are fixed labels and you want to classify an image into those labels. Regression could be some kind of a position, like detection. If you're doing object detection, then you have to say where exactly, what is the coordinate. So it's a real number, and then you have to do a regression. In that case, you just, yeah, you can directly do L2 norm minimization like that during training, basically. But anyway, so this is general structure of multi-layer perceptron. And what this various hidden layer corresponds to is like this kind of extraction. So the first hidden layer generally, if you are looking at an image, then the first hidden layers will extract edge-like features. So all it is doing is finding out edges at various orientation. The second hidden layer might be doing is combining these edges into contours. And the third one might be doing it into parts. So like generally this is the, like as you go deeper and deeper, this is what is happening. So the first layer extract edges, simple image features, and then in the middle layer you're combining them. And finally in the end, you keep on combining till you start seeing more like parts of this object. So somewhere you will see the wheels and all. So this kind of this. And finally, they follow up this with the classifier. And this is more or less the structure. The reason for this hidden layer is this kind of low-level, mid-level, high-level features. So in our brains also, we have V1, V2. There are various layers which are doing kind of similar kind of task. So it is motivated from that fact. Okay, so actually CNNs, not CNN, neural networks, they have a lot of variations, like depending on what the type of data you have. So the popular model one is called multi-layer perceptron, a fully connected layer where each node is connected to every other node. But there are other variations, so convolutional neural network, then RNN is there, recurrent neural network, then autoencoder models are there. So here we'll mostly look at CNNs, which are mostly the one, at least the examples that we look at. This is the one neural network that is used everywhere for those examples, for solving those examples. So now the question is, what are CNNs? How is it different from the multi-layer perceptron? So if you look at image, for example, so if I want to solve it using multi-layer perceptron, so how we looked at is, it was a vector of input. So the first thing that you need to do is vectorize it. So for example, if the image size is something like this, then if you vectorize it, it's like 40,000 into 3. So it's like 1.2 lakhs or something. So, and then you will have multiple hidden layers. For example, if you consider, or let's consider it's, so multiple hidden layers like this. So your input itself is like 1 lakh nodes, and then the hidden layer could also be 1 lakh, and then it's like 10 raised to, so if we count the number of weights, so if this is 10 raised to 5, and this is also 10 raised to 5 nodes, then the number of weights is 10 raised to 5 square. So number of weights that we need to learn. So it will just go out of memory as well as out of computation power. So we cannot use for this kind of images, for image object recognition and all, we cannot use the simple multi-layer perceptron. So that's what, so we need to use something called as CNNs. So let's see what it is doing. So we need to reduce, the main thing is we need to reduce the number of weights that we have. So this is what the multi-layer perceptron, a fully connected layer is, where this is the input layer, and these are, let's say, the hidden layers. And each node is connected, each input node is connected to all the hidden layers. So it's a fully connected layer. So which means here, for example, there are 7 nodes, input nodes, and 3 hidden nodes. So there are 21 parameters that we need to learn during the training. So if we want to reduce the number of weights, then one way is to use this kind of thing, where we say that not all the input node is connected to all the hidden layers. Rather, it is the neighboring nodes which are connected to one hidden layer, and these. So there is some kind of a spatial context, which in images it's very clear. For example, what we can say is all these inputs, we can say the 3 by 3 blocks of pixel will be connected to one node, one hidden node, and then the next 3 by 3 block of pixel will be connected to the next hidden node. So like that, we can use this local connectivity. And so instead of saying that each node is connected to every other node, we can just say that locally it should be connected to one hidden. So something like that. And by using this, we are reducing the number of parameters. For example, this has only 9 weights, which are much smaller in number than, basically it is storage as well as runtime efficient. Okay. So this is one reduction that can be done using this local connectivity. And images have them naturally, because generally, if you see images, they are correlated in a local neighborhood only, something like that. Generally, the correlation dies down. So instead of trying to see everything, you can just see locally the pixels, and then you can infer something from there. So that's one thing. The other thing is, if we still further want to reduce the number of parameters, for example, now it is 9, one thing that can be done is weight sharing. So instead of every time saying that these weights are all independent and different from each other, we can say that whatever these weights are, we are repeating them, kind of. So this will further reduce the number of parameters to 3 parameters, which is much faster than both these alternatives. So this is called weight sharing, or parameter sharing. And if we see this is nothing but the convolution operation. In convolution, there is one filter that we move across the image. And that filter is basically, those filter is defined by these weights, and then we are moving it across. So these are the convolutions. So basically, the convolution layer is what is helping us in reducing the weights. And it's very, very suitable for images. Even for images, it's a 2D signal, but if you go for speech also, it's 1D signal. There also you can do 1D convolution. But obviously, the gains for 2D is more than 1D. So it's very popular. And so these are the two things. This is a generic CNN. So you have the input channel, so which could be the RGB channels, so 3 channels of the image. And then you do this convolution. So this is the filter, so 3x3 or 5x5 filter. And then and you move it across, across this image. And every time you compute, you do this linear combination and compute this channel. So this is the output channels. And you can do this with various filters and obtain many, many output channels. For example, these filters could, for example, one of the filter could correspond to detecting horizontal edges. And then if you just do it, it will find out where all there are horizontal edges in the image. Then the other filter could be vertical image. It will find out which all pixels have vertical edges. And then you can do 45 degrees, 30 degrees, whatever. And this will give rise to this output maps. And each channel basically corresponds to some set of information. So this is the most basic block of CNN. This is the convolution layer. And in general, it is like this. So it is always convolution layer followed by some kind of a nonlinearity. So this nonlinearity is very, very important. So this is ReLU. So, but it could be something else also. People have used sigmoid and all. But so without this nonlinearity, it will actually not work. So all this CNNs and all the deep learning networks will fail if you don't have this basic nonlinearity. So this nonlinearity is very important. So generally, it is always convolution followed by the nonlinearity. And then there is also pooling, where in the sense that you reduce the channel size. So the spatial dimension, you can reduce it. And then again follow it with convolution, again pooling, like that. So the goal of pooling is that you're reducing the size, like as these are the feature maps. So you're reducing the size, spatial size of the feature map, which helps in 2 ways. One way is the computations are reducing because you are getting smaller and smaller. The number of parameters are reducing. The other way is that you look at a bigger and bigger context. For example, if you look at a pixel here, it will map to something much larger here. Or if you look at a pixel here, it will map to a larger area, and this will in turn map to a larger area in the image. So it is actually looking at a bigger and bigger context, so as you go further and further, so because of this pooling. And therefore, you see the image as a whole, almost. It depends on how much context you can see. And finally, this is followed by, so convolution, nonlinearity, pooling, like this. You repeat this same block again and again. And finally, there are some fully connected layers. So this is nothing but the multi-layer perceptron, where each node is connected to every other node. So you need to flatten it. So this might be, it is a 3D voxel. So first of all, you make it like a vector. And then you have like this kind of fully connected layers, where each node is connected to every other node. So the main reason, and then it is followed up with a classifier, for example, softmax. So the main reason why we have the fully connected layer is you need to look at the full context. So if you want to classify an image as a car, you need to look at the whole image. So therefore, this fully connected layers helps in looking at the whole image. And then you follow this up with the classifier. So this is the overall architecture of CNNs. And yeah, this is a simulation, like what exactly the convolution layer is doing. So this is the filter. And we can see this is the kernel, like 101, so something like that. And the fixed kernel, the same kernel is being shifted and convolved, basically. And then this is the output that we get. Okay, so it's obviously leads to reduction in weights and all. The other layer is pooling. Pooling means that we look at a 2 by 2 pixel, a certain number of pixels, and then we get one number out of it. So this is max pooling in the sense that if you look at this red block, so what we do is we look at the max value among them, and then we say this is what it is. And same operation we are doing. So this is a max pooling, which reduces the size. So these are the two important components. And then we have the fully connected and the softmax layer. The fully connected layer is this, which is nothing but the multi-layer perceptron. And this is followed by softmax. So softmax is just one way of doing classification. You could have, you could have used any other classifier also. For example, you could have SVM. You could have used SVM. But generally, softmax is preferred because it gives end-to-end training. If you use any other classification, then you may not be able to do end-to-end training. Like you would like to, train all the parameters together. So this is overall architecture. So convolution ReLU like this. So this is generally what the CNN looks like. So what next we'll look at is, okay, so then we look at, so now the question is how do we use this CNN for doing object recognition, detection, all these tasks. So first we look at recognition, where you have an object in the, basically the image is like this, and then you have to say which of the object it belongs to. So there are some labels which are already given, and then you have to say which level it belongs to. Okay, so this is one of the important problems which we do all the time. Like we have to do object recognition, otherwise we can't even interact with the world. So how do I do it? Again, this we have already seen. The computer only sees intensity values. It doesn't see it as an object. And how do you make it look at it? And then these things we have already seen. The challenges are this viewpoint variation, illumination, deformation. So all these are challenges. Occlusion, background. So basically you need to do the recognition in such a way that it is invariant to all these kind of variations that you see. Okay, so there are a lot of progress which have happened. So these are the these are the non-deep era. So these are shallow networks, or basically the traditional way of solving. And this is what this is showing is the error. The y-axis is showing the error, and the x-axis is showing the various evolutions of deep learning, or it starts with traditional method. So for example, the error in recognition. So it actually the error, this is a top 5 error classification, which basically means that whatever classifier or whatever vision algorithm we decide on, and we look at, so given that image, we'll ask it to output the top 5 predictions that it thinks that object is, and then we'll see whether the ground truth class belongs in the top 5. If it is not, then we say it is making error. So what this y-axis is showing is top 5 error in that sense. So what we see is that this error was very high. So this is one particular data set. It's called ImageNet, which has like 1,000 classes. Each class has some 1,000 images. And the task is to train using this data set and test it on a different set of images. So this error is very high. It's not even, it's a top 5 in the sense that all, like 25% of the time, whatever I predicted is not even there in my top 5 predictions. So this error was very, very high. So this was the first, like around 2012, is the Alexnet. So this 8-layer network, it has 5 layers of CNN and 3 layers of fully connected. So this reduced the cost by like 9% or so. So it was a huge reduction compared to previous years when it was almost constant. So this was followed by more and more. For example, this is a VGG net. So this has like 19 layers, and that also reduced the error significantly. And again, this is Google Net or Inception. And this is ResNet, which further reduced it. So this is like 150 layers, something. So it kind of shows the power of deep learning, like where it was before the deep learning era and where it is now. And these are some of the networks. So LeNet was the old, it was very simple. It's like 2 convolution layer and 2 fully connected layer. But it was not doing as good. So SVM will beat LeNet kind of. And therefore, it was stuck kind of. So after that, Alexnet is the one which basically started the deep learning era in computer vision. So it's like, so this we already discussed. It's like 8 layers. This is followed by VGGNet, GoogleNet, and ResNet. And we'll quickly look at each of them, a little bit more details. So this is what the Alexnet is. So this has like 5 convolution layers. And each layer had some, like for example, the first filter size was 11 by 11. Then it was 5 by 5, and then 3 by 3. I mean, it followed thrice we did this operation. And this was, there are pooling layers also. So the main innovation actually in this Alexnet is these 3 things. So ReLU as a nonlinearity. So before that, people were using sigmoid or tanh as a nonlinear unit. So ReLU is rectified linear unit. It's basically, it is something like, it's like an identity function, but anything below 0, you clip it to 0. Anything above 0, you keep it as it is. So if it is like 5, then you keep it. If it is anything below, like for example, -2, -5 or anything, you clip it to 0. So you make it 0. So basically, make the negative components to 0 and positive you allow as it is. So that's the kind of nonlinear that ReLU is. And with that, it has seen that there's a lot of the training is much more easier than if you use a sigmoid as nonlinearity. The reason for that is the sigmoid has the saturated regions. So the sigmoid function, it looks like this. And in this saturated region, if your parameters go in this saturated regions, then basically the gradients will be 0. And so the major way of learning, training a deep network is called gradient backpropagation. But if it becomes 0, then all you backpropagate is 0, and so you cannot train it well. So the ReLU is much better in that sense because at least in the positive, when it was positive, the gradient was all 1. So you can easily do the backpropagation. So this was one of the major findings. Then there is dropout regulation. So before that, we can look at data augmentation. So both these techniques are regularization technique, which prevents overfitting. So since the number of parameters are huge, like of the order of millions, so though the convolution parameters are smaller, but if you see fully connected layer, like it's like 4,000 cross 4,000. The number of nodes here is 4,096. And this has 4,096. So 4,000 cross 4,000. So this itself is huge number. So these many parameters, if you directly try to estimate it, what it will do is overfitting. Like it will fit exactly to the training data, but in testing it will perform very poorly because of the large number of parameters. So these regularization techniques are basically to avoid this kind of overfitting. So one is data augmentation, where all you do is rotate, for example, given an image, so basically it corresponds to increasing the data size. So I have some training data size, but I want to make it much, much larger because the number of parameters are huge. So my training data should also be huge to prevent it from overfitting. But we may not have so many images for training. In that case, you just take this image and you do various rotations, scaling, shifting, all this operation, and from there you can increase the data size to, like if you do 10 operations, like the data size will become 10 times more. So these are data augmentation technique which they used. This is one of the things which they use for regularization. The other thing is called dropout, where while training they will drop out some of the nodes. And then they will learn it, like every time they learn it, they will drop out some different kind of nodes. And this will make the network robust to this kind of overfitting. So we can't go in details because this is more involved topic, but these are the main reason why Alexnet did much better than previous networks. the LeNet basically is because of these three contributions, and because there were GPUs also, advent of GPUs also one of the contributions. So this is basically the algorithm which started this revolution kind of, and then this was followed by VGGNet. So VGGNet is like more number of layers, so it is 16 or 19 layers, and but it uses the filter that uses a very simple. It actually uses all 3x3 filters. So all of these are 3x3 spatial filters. If you look at Alexnet, it was using larger filters, for example, 5x5, 11x11. And this larger filters helps us in looking at a bigger context. But here, they were all using 3x3 filters. Now, the question could be that, how can I look at a bigger context if I'm using a filter size which is very small? So this is explained here, that if you stack two 3x3 filters, it is equivalent to having a receptive field of a 5x5, or the context of a 5x5 filter. And if you stack three of them, then it is like looking at a 7x7 context. So this can be seen from this figure. So first of all, we can ask that what's the point in doing that? Why can't we directly use 5x5 receptive filter? So instead of saying that if we stack two 3x3 filters, it is equivalent to 5x5, and then we keep on saying that let's use a lot of 3x3 filters. The counter question could be, why not directly use one 5x5 filter instead of using that? So then the question, the reason for that is, if we look at a 5x5 filter, it has 25 parameters, whereas this one has 9. And if I use two of them, then it is like 18. It is still less than 25. And same logic you can see here also. This is like 49, but this is like 9 into 3, which is 27. So it's like half of this. So definitely there is advantage. Now to see how the two 3x3 filters will simulate 5x5, at least the receptive field, you can look at this. So for example, if you consider this pixel, the center pixel, then when we do a 3x3 convolution, it actually looks at all this 3x3 neighbor. So in this layer, it will look at this. And if I think of, so this is like the second layer. So I'm looking at the second convolution layer. So now if I look at the layer previous to it, for example, if I look at this pixel, this itself is obtained by convolving a 3x3 filter. So in that sense, it looks at a bigger context. So for example, this pixel is obtained as a linear combination of this pixel in one layer. But if I look at the layer before, this pixel itself was obtained by a linear combination of this pixels. So overall, this pixel actually, if I repeat convolution twice, then this pixel actually sees all these pixels. So therefore, the receptive field is 5x5. And this you can increase. So there is an advantage in doing that. So that's why the network was very simple. It is basically a lot of 3x3 convolution layers. And they showed it is easier to train because the number of parameters is less, at least compared to if you had used these kind of bigger filters. And there is also more nonlinearity, because after every 3x3 convolution, there will be a nonlinearity. So the number of nonlinearity also increase if you use just 3x3, if you just stack the smaller filters and less parameters. So this was the advantage. So this was followed by GoogleNet, or it's called Inception. So here, what they are doing is, so one way is to go deeper and deeper to look at, for example, here we are saying that we need to look at bigger and bigger context or receptive field. And if I can use simple filters and try to increase it, so which basically means is to go deeper and deeper. But if you go deeper and deeper, it is very difficult to train also. So what this GoogleNet did was, or this Inception model is basically saying that instead of going deeper, can we increase the width of the network? So that's the idea. So the idea is that I can maybe convolve. So the goal is also, there are two goals. One is to reduce the depth of the network, because then learning the parameters is difficult, because the parameters are trained using backpropagation. And if the number of layers are very huge, then the gradients will die down, which is called vanishing gradient problem. So that's one of the reasons. The other reason is that we also want to look at various contexts. Given an image, I want to look at the image at various scale. Because, for example, object recognition, for example, if I'm interested in finding a car, the car can be at various size. The image, I mean, it can be like, we can take an image in such a way that the whole image has the car, or I can take an image which is I'm farther away or zoom out and the car is occupying smaller number of pixels. So basically it can occur at various scale, and this convolution, changing the convolution size will allow us to look at the image at various scale. So it is kind of a multi-scale approach. So this is the second reason for using this kind of a wider network. And then you concatenate all these responses, and then, so this is one basic block, and then you repeat. So for example, this is one basic block, and you repeat it some multiple times. So here it was repeated 9 times. So like that. So, but it had some 22 layers and all. And this was one of the major inventions or discoveries. This was followed by ResNet. So this was, so the question was, till here it was like the number of layers, if you see it is like 16 and then 22. So this ResNet, the goal was that we really want to increase it much, much larger. So they wanted to target something like hundreds of layers or even thousands of layers. So now the question is, can we do that? Can we train such a big network? So if we just simply stack layer after layer of 3 by 3 convolution, let's say, that's not going to help, because here is one simulation. So this is a 20 layer network, and this is the training error it is showing. So it should decrease with iterations. And what it is found is that if I use a 56 layer, the training error is larger than the training error of a 20 layer network. And this is corresponding testing error. So this is 20 layer, and 56 layer is again higher. So generally what we expect is that as we increase the number of layers, it's more and more flexible. So at least we expect the training error to go down, not increase. Because if I use more and more complex model, I should be better able to fit my training data. It might be that I might do overfitting and testing error can increase, but at least the training error is expected to be lower. But in this case, that also is not happening. So, and the reason for that is basically it is not able to train it. So train it in the sense that, again, the training is done using gradient backpropagation. And what happens if you have too many layers, then the gradients die down. You're kind of doing powers. So if I have, for example, 0.5, and let's say there are 10 layers, so that point, if the gradient value is 0.5, then when it goes through the 10 layers, it will be like 0.5 raised to the power 10. So it has almost gone to 0. So that is what happens in this is called vanishing gradient problem. So this is what is happening if you have larger network. So basically, it is very, very difficult to train a deeper network. So, and this is a thought experiment which is showing that why a larger network should not have this problem. So for example, a deeper model should not have higher training error. And what they're saying is that, for example, let's say this is the 18 layer network, and this is the 34 layer deeper network. And what I can do is I can just introduce here this extra layer, which are nothing but identity layers. So at least then the training, then the training error should be equal to this. In fact, if we are if we are able to properly train it, it should be lower. But at the worst case, it should be equal. But what we were saying is that it is not even equal, it was larger. And that's what it is saying, that this is because of that error backpropagation. So this is the, but if we somehow could use identity, identity modules, it should remain same. And that is the idea of this ResNet block. So ResNet block, what it does is, let's consider these 2 layers, stacked layers. So if I use a plain network, it's not plain, this T is a mistake. But if just a simple network, then it is like you stack these layers. And the goal is that we want to go from x to some output y, which is h of x, some function of x. So this is what traditional network is doing. And what this residual net does is instead of directly trying to go from x to h of x, what it does is it's also have a identity mapping. So it basically brings this x here, just from here. It's a skip connection, so it brings the x here. And then these networks, these weights, are trying to learn only the residual. So instead of directly trying to learn the function from h of x, it tries to learn the residual, which is f of x. So it brings the identity, which is x, and then just tries to learn the residual. So in case that this h of x is an identity, in that case, we don't need to learn anything because this x will take care of it. And in case the h of x is close to identity, then also it is easier to train this network than directly training the previous network, because then this residual values will be small. So this is the idea. So using this kind of identity or skip connection, so this is the residual block, one block of residual network. So it uses this kind of skip connection, and that gives rise to this. It uses this power of identity mapping. Actually, it also helps in error back propagation, because when you're propagating the error back, it can take this route. And so the gradient won't decay as much. But if it takes this route, the gradient will decay more. So this is the reason why if you use this kind of residual block, then you can have a much longer or much deeper network. Yes. And this is a very, very simple network. So this is the plain net, if you use like this. And this is the residual connections or skip connections, which are using this. So this is the ResNet. And because of it, it is able to train much better than if you directly try to train this. Okay. So these are the various versions, and the ResNet, and now there are versions like combining ResNet and Inception net or Google net, and all these versions are there. There is DeepNet, but these are almost close to the state of the art. So till now we looked at various CNNs and various versions of it. For example, Alexnet, followed by VGG and Inception and ResNet. So these are all for object recognition. Like given an image, we have to categorize which object it is. But we can also look at detection. In detection, the goal is that we are given an image, and we have to find out what all objects are there, where exactly they are located. So this is the problem of detection. So we have to find a bounding box. Wherever there is an object, we have to draw a bounding box around it. So like this. Okay. So there are two tasks basically. One is to find out the bounding box, which is finding out the coordinates of the bounding box. And the other thing is to find out the object within that bounding box. So these are the two tasks. And this is obviously more complicated than just recognition, because in recognition can thought of as a sub-problem of detection. In recognition, generally people will give you the proper cropped image. You need to check for all of them. So what is the problem with that? The problem is that you have to scan through various positions. So if you have a 100 by 100 image, almost you need to scan for 10,000 locations. So 10,000 times you have to solve this problem. So which is very, very computationally slow. And also it's not just one window size. The objects could be at various aspect ratios. So you cannot just try out this aspect ratio. You should try square, rectangle, and all those things you should try. So it's very, very computationally involved. So there's no way you can do it. Maybe if you have a very fast classifier, you can do it, but not with deep networks, because they will take some time. So if I use, for example, these are difficult. I mean, they are slow only, right? So we cannot use deep network and this kind of a window operation. So the alternative to this is to find out kind of regions which might have objects. So these are called region proposal algorithms. So which is basically given an image, it will try to find out only a small subset of regions where the algorithm thinks there is an object. And then all you have to do is pass on these regions through a classifier and see which class it belongs to. So for example, this is the philosophy followed by one of the object detection algorithm, which is known as region CNN. So in which what is done is, given this input image, it will extract some regions where it thinks there is an object. And this was done by a separate algorithm. It is not a deep algorithm. It's called Selective Search or some algorithm like that. So which was all it was doing is giving out proposals or regions where it thinks there is an object. And then what you do is, given each of these proposals, you first of all warp it to some size, predefined size, and then pass it through a CNN network, for example, Alexnet or VGG. and then you can do the classification problem. Solve the classification problem. And for example, generally the algorithm they were using, it gives around, for each image, it will give around 2,000 regions where it thinks there is an object. And you have to repeat this 2,000 times for each window. First of all, they could be of various aspect ratio, but you need to warp it to a particular size because of the architecture they are using, which has fully connected layers. So if you have fully connected layers, then the input size is fixed because of all this architectural constraint. So every time you need to warp it to this size and then pass it through and do it. And you have to do it as many times as there are region proposals. So which is, again, very slow. So that's and not only you have to do the classification, you have to also say where, like, though the region proposal is giving the bounding box, but you have to still correct for it. So you have to also do a regression where it will output what exactly is the corrected or rectified image location, which basically is a 4-dimension output where you have to say what is the XY location here and what is the width and height of this box. So this also you need to solve. So, but the problem with this algorithm was there are like thousands or 2,000s per image using the selective search algorithm. And you have to run, every time you have to run CNN through those 2,000 basically regions. So that's very, very slow. So then what is the solution? So basically there are 2 solutions that can be thought of. One is that instead of doing CNN, so like for example, this is, and then depending on where the bounding box is, find out like the bounding box is in the image, but then somehow I can go and find out how the bounding box is getting transformed as it goes through the various layers. I can go to some layer which I have decided to extract the features from, and from there I can have my classifier. So that will definitely, speed up the algorithm at least 2,000 times. So that's one of the proposals, one of the improvement. And the other improvement is, instead of using a different algorithm for doing this proposal, why can't we use the deep network itself to propose this kind of regions? So the first modification where you pass it through one CNN, only once, is known as fast CNN, fast RCNN. And the second one, where you're also using the region, using the network to do the region proposal, is called faster CNN. So these are the 2 modifications that happen to the algorithm. So overall, the idea is this, that we do, given the image, we pass it through the convolution layers only once. And then there could be a region proposal network which will try to find out where the objects are. And this will follow up. So once I know so this region proposal network will basically tell me where the bounding box is. Once I know the location of the bounding box, for example, this car, then I will basically try to find out where exactly, what is the region of interest in this particular layer from which we are taking the features. And then I can pass, then you need to do some kind of a pooling in the sense that because these shapes can be of various sizes, these boxes could be of various size, but when you pass it through a classifier, again, the size need to be fixed. So you need to do some kind of a warping, which is called ROI pooling. But once you do it, then you can pass through the classifier and find out what class it belongs to, whether it's car, building, and all those things. So this is the idea. So basically, there are 2 steps. One is the region proposal, which is finding bounding boxes. And the other thing is, once you have the bounding box, then you want to classify it. Okay. So this part is classification, which we have already seen. So this region proposal network is the new thing. So kind of what it does is, it looks at some particular layer. So generally this layer, once you go deeper, this layer, this spatial size will be much smaller. So it will be around 50 by 50. And then what it is done is, you look at each pixel in that 50 by 50 feature space, and then you try to find out whether there are objects in that pixel. Not the pixel, but you look at bounding boxes around this pixel with various aspect ratio. And then try to find out whether there is any object. So for example, if you try out this aspect ratio, this particular size, then you ask, then there will be a classifier which will tell us whether there is an object there or not. If there is an object, I will keep it as my region. If it is not, I will throw it away. And this way, I will try to go from one pixel to another pixel and every time find out whether there is a possible object or not. So only those pixels where it seems like there is an object will keep, or those bounding box where there is an object will keep, others will throw away. And so this is the way this network is done. So once we have it, then we basically go to the other one and where we directly classify. So the first one, all it does is finds the bounding boxes, which is, so the first network is all it is doing is there any object there and where exactly it is. And the second network is classifies this object. So this is the, basically the, I mean, one of the, this is the faster RCNN. This is one of the best performing algorithms. There is also YOLO, which is competing, and there are SSD, some other variations are there, but this is one of the, if not the state of the art, then close to the state of the art. So this, so with that, we'll look at, so till now we were looking at semantics. So what we looked at is object recognition followed by object detection. So but both of them are semantic tasks. So the next thing that we look at is the metric task. And this part will be smaller. So here we are interested in estimating depth. So for example, this is a goal that we are given RGB image, one image or multiple image, and from there we want to find the depth map. So per pixel we want to estimate the depth map. So this is the goal. So basically the goal is that how far the object is from the camera. So, and this has various applications in autonomous navigation, in virtual, augmented reality, scene understanding. All these are various applications why we need depth. So, and the most famous way, or the most used way is the stereo, depth from stereo. So where you take two images like this, and then from there, and these images are shifted versions, and from there you try to find the disparity between them, or from their depth. And this is the principle our eyes also work on. So we have two eyes, and if you close one eye, then you will see, and if you hold the object close to your eye and then close one eye and then open and close the other eye, you will see that the object moves. So there's a disparity, and that is the cue for depth. And the closer the object is, the disparity will be more, and further it is. And that is what our brain is using, and that's how we compute depth. So the stereo, depth from stereo is basically doing what we are doing. So that's the thing, and this is the principle. Like for example, if let's say I'm interested in this object, and if I can locate that same object as 2 points in the two images. So this is my first image, or the camera position 1, this is camera position 2. If I can say that this point in the scene is imaged at point P here and point P prime here, then the problem is very easy, because you can then back project. So this is the camera center. So you can assume it's a pinhole model in the sense that all the rays has to pass through this origin or pinhole. So if we assume that, then it's very easy, because what I can do is, since I know that all rays has to pass through this, and I can then join this line and extend it, and we know that my 3D point should lie on that line somewhere. I can do here also, and then wherever it intersects, we know that that's the object. So this is called triangulation. So if I know my camera position, if I know where the camera is located, then I can easily do triangulation, a back projection, and get my 3D point. So that's the basic principle. And it can also, like for example, the question could be, so the main task in stereo is then to find point correspondence. Like basically find where this point P in this image, because we don't have access to the 3D. All we see is the two images. These are the only input. So all we need to do is, if I see some point or some pixel here, I should be able to say where that pixel has gone in the next image. If I can do that, then I can get my 3D. So this is called point correspondence. So all we have to solve is solve for this point correspondence, and then doing 3D is nothing after that. So the main problem here in stereo, depth from stereo, is solving for the point correspondence, which basically means that given this point, I have to search throughout this whole image where it has gone. So this can be computationally very cumbersome also, and it can also give rise to a lot of mismatches, because if this point I'm searching all over the image, then there is high chance that it will see many such points. So what can be done to solve for this is something called epipolar constraint, where instead of searching for the whole image, so this is the point, and I want to see where it has gone. So instead of searching for this point all over the image, I can actually search only along this line. And this is called epipolar line. So I won't go in that details, but the simple idea is that if this is the point I'm interested in, I know that the 3D point, the actual 3D point will lie on this line. And this line then projects onto another line on this image. So this is called epipolar line. So all we have to do is search along the epipolar lines. So instead of searching over the whole image, just search over the epipolar line. So it simplifies the problem. At least it simplifies the point correspondence. So this is what the traditional vision is. So yeah, once you find this matching, and then you can do this. Yeah, so this you have already seen. So this is more like people have used deep learning. So this is a recent, so generally people do this only. So traditionally this is what has been done. So for stereo, first solve the point correspondence and then do triangulation. But what can happen is it may not be easy to find even the right match. So here they are doing, so this basically this work uses DeepNet for solving this problem. So the goal is that I have a left input patch, and then I want to find out, and given a right input patch, I have to find out whether these two patches belong to the same objects. So this is a network just to find out whether it belongs to the same objects. So all it does, it passes through some convolution layer, and then it produces some features, and then it, based on these features, it tries to say whether the two patches are same or not. So it's a binary classification task, and it uses Siamese network in the sense that the parameters are shared here. So it's a CNN network, basically. So that's why it's called, so matching cost CNN. So this is the, I mean, there are two versions of it. One is called the faster architecture, where all you do is, given these two patches, you compute some features, and then do dot product between them to find the similarity, how similar they are. The other one is more accurate in the sense that you again pass them through these feature layers, and then concatenate, instead of doing dot product, concatenate it, and then do some fully connected layers. And that will again compute the similarity. So the goal here is, given two patches, one patch from the left image, another from the right image, all we have to say is whether they are same or not, whether they correspond or not. And this task is being solved by this CNN. Okay, and because once you do that, this task, then triangulation is very easy. So this is one of the techniques. Okay, so this is anyway. And these are, it shows that some of the results. So this is my input left image, right image, and this is the ground truth depth. And this is what these architectures are computed. This is using the fast architecture. This is accurate. I mean, they're almost same, and it is a little better than this some traditional way of computing depth, which has some errors here. So the errors are lower, and we can see that they're almost close. So any of these architecture can be used. So this is like, so solving the depth from stereo using the deep network. And this has also been extended to solving depth using just one image. So now the question could be that from one image, how can we even compute depth? Like stereo, or our eyes are using the stereo skew, right? Like in the sense that it finds the disparity. But in one image, where is the depth Q? And so if the depth Q is not at all there, then how can we expect? So actually the depth Q are there. For example, if we look at this kind of image, then we know that these lines are actually parallel, but we can see they are like converging. So this is a Q for vanishing point Q. It's called vanishing point Q, which gives us a Q for how far the object is. So there are Qs like that even in a single image. So this is one of the Qs. And there could be other Qs, like for example, the size of the, for example, if you look at here, definitely the smaller car basically means that it is further away. So we use size Q also. So we know what the size of the objects are, and if we see very small, then we know that it is further away. Then there are occlusion Q. For example, this object is occluding that object, so this object must be in front of that object. So there are all these Qs. So this kind of parallax Q or vanishing Q, then this kind of size Q, then this kind of occlusion Q. All this can be used to obtain depth from a single image also. And this was one of the major, I mean, this traditional method is very difficult to do. But with deep network, it has been shown that even with one image input, also you can compute very good depth map. So this is one of the major developments. So this is one way of doing this. So basically, given the image, it will first compute some coarse depth map. All it does a lot of pooling, and then from there, all it tries to do is a global depth map. And then it uses this global estimated depth to further refine it and get a refined depth map. So it's basically deep, I mean, it requires a lot of training in the sense that you have to give a lot of such image and corresponding depth map. So supervised training. And with that, you can try to learn this kind of a network which will map this image to the given depth map. And you can train it, and that's the goal. So basically, this particular algorithm, it uses two scale. First, it will estimate a coarse depth map, and then it will refine it. And yeah, so coarse network predicts overall depth of the scene, and then the fine network refines the global prediction. So the depth map is 1/4 of the resolution of the image. Yeah, so this gave kind of good results only, and okay kind of results. So the coarse estimates were very coarse, as you can see. Fine estimates are better, and they have at least some similarity with the ground truth, which is good only. I mean, in the sense this is a very challenging problem. To even come to this stage is also quite good. So this was followed up with other kind of works. So one problem with this kind of approach is that it requires supervised training, in the sense that you have to give the image, and you have to give, during training, you have to give the image and the depth map. And then the network will try to learn the mapping from this image to this depth map. So it's a supervised, which means that we need to have access to the depth map, which is not easy. Actually, getting depth map is not at all easy. I mean, there are Kinect and all, but it will have a lot of holes, a lot of noise. So how do you get reliable depth map? So instead of that, the other approach could be, can we do away with this kind of depth map, and can we just from the image, can we get the depth map? So that's the goal here. So what they do, what this unsupervised method does, it uses stereo. So where is it? So it uses the left and right image pairs. So basically it uses stereo. So all you need is a stereo data set. And so what it does is it takes this left and right. So during training, it will take the left and right. And what it will do is from the left image only, it will try to predict the depth. So it is doing monocular, because all it cares is take the left image and then try to compute the depth. But the error that it does is, once it computes the depth map or disparity, it will then warp the left image according to that disparity to something which looks like a right image. And then it will take the error between this warped right, I mean this ground truth right image and the warped right image. So it is an unsupervised method, in the sense that it doesn't require explicit depth. All it requires is two images, and it takes, actually all it does is, it does from one image, it tries to predict the depth, but while minimizing the loss, it also uses the right image. And what it does is, it takes the left image, and according to the depth map, it warps it and then minimizes the error between the right image and the warped right image. So this is an unsupervised technique, and this kind of training is, I mean, that's what they have shown, that this also produces quite good result. And this kind of obtaining stereo data is much easier than obtaining the RGBD data, like depth data. So this method is better than the previous one. So at test time, the network only predicts from the left image, one single image, because it doesn't have the right image at that time. So it's a single image depth estimation technique. And this is what the kind of results it is getting. So this is a predicted one. So it's quite good. So again, this is actually from one image only, but it is giving quite good results. So what we have seen here is that how we can predict depth. So we looked at stereo techniques, how deep learning can help in that, basically in solving point correspondence. Then we looked at, from a single image, can we get depth? So there are two techniques. One is supervised, where you need the depth data also while training. And the other one is where you don't need depth data, but you can have a stereo image, and then you can do it. And so this is more or less overall what we covered. That first we looked at CNNs, the various versions of CNNs, how it can be used for solving object recognition. Then we looked at how again, the CNNs, or what is the network modification we should do to solve the object detection problem. So this is a more challenging problem than this. Here you have to find the object regions also and then do the classification. And then finally, we looked at depth estimation. So this is from stereo, and this is from a single image. So with that, I will stop.